让他们。那行为开始了。好，那我们开始吧。欢迎参加 AI 加生命科学专场，我是本专场主持人许东。非常感谢各位嘉宾和朋友的莅临现场，然后给予我们很大的支持哈。这个300多年前呢，牛顿把物理变成了数学模型；8年前 ，OpenAI 把语言变成了数学模型和编程语言。那么现在这个深度学习和大模型时代，能否来助力把生命现象变成数学模型，并且在这个模型上可以实行这个可控的操作？那么今天我们有3个报告呢，就是在这方面呢，做一些基础研究的探讨。那么这个ChatGPT 8年前开始以来呢，就是这个非常火爆哈，这个会议呢有很多的这方面的探讨。那么我呢，这个就是作为第一个报告人来讲讲我们这方面的探讨。我是这个做生物信息学的，过去是物理学出身，然后90年代来到美国，然后在 UIUC 拿的物理学博士，后来呢在橡树岭美国癌症研究所等地做了研究，然后过去20年呢是在美国密苏里大学哥伦比亚分校做这个教授，然后过去的10年呢，我专注于用深度学习的方法来研究生物问题。那么我今天呢，就是讲讲我们最近的工作，就是所谓这个以提示工程为基础的这个分析，就对这个医学图像和这个文本的分析。那么昨天这个潘老师也讲了这个大模型的这个时代哈。那么从这个大模型这个划分来说哈，那么有一种划分我觉得我比较欣赏，就是把机器学习分成4个阶段。第一个阶段呢，就是所谓这个人工的这种特征，就是所谓特征工程的这种阶段，比如说 SVM 或者简单的神经网络。那么第2个阶段呢，就是所谓构架工程，也就是说用这个图像是我们用这个原生的这种特征，然后呢，在这个深度学习的网络上去做各种的调整。那么后面呢，就是所谓大模型时代。那这个分法呢，把大模型时代又分成了2类，一类呢就是所谓目标工程，也就是说像 BERT 这些模型，它是一个大模型，然后在上面做这种各种预学习啊，各种这种微调啊，来适应各种的这种应用。当然第4阶段就是所谓这个提示工程哈，就是说那是在一个基础模型上做各种各样的这种应用，比如说从这种 zero shot 到 few shot 的应用。那么现在大模型很多，但是能称之为基础模型的其实并不多。我个人认为，一个基础模型至少得符合3点。第一点就是说它可以被提示，有各种端口容易提示。第2点呢，就是说它能够适用于非常广谱的下游应用。如果它只能几种少数的应用的话，这不能称为基础模型。第3点就是说它必须有智能涌现。其实多数大模型并没有展示出智能涌现。那么智能涌现必须有超大的数据训练，才能从量变到质变才能实现。那么这些大模型的过程呢，就真正可能把人工智能带入非常广谱的这种工业化时代。这个就非常像这个计算机硬件哈。那么早期的时候，我们有这种电子管想象过，就是说包括晶体管等等的哈。那么现在我们用芯片，其实就是第4阶段，就是提示工程。也就是说，我们芯片并不打开，也不微调，也不用去做各种设计，只是在芯片上用很少它的一部分功能。但是这种东西可以批量生产，造价可以非常低，应用非常广谱。 那么我们这个时代呢，也是这样，就是说有了大模型，可能就像芯片一样，只有极少的公司在做这个大模型，而大部分的人都是在这大模型上去做各种应用。那么这个时候呢，你的机器学习变成了一个黑箱。过去呢，这个很多人批评深度学习，就说它是黑箱。但是呢，在提示这个工程里，黑箱可能是一件好事，因为你不需要关心里面的复杂度，就像你用一个手机一样，你只关心界面跟它交互，你不用关心这个里面手机是怎么做的。那么提示工程也有各种方式，我今天会讲这个2种模式，就是一种所谓叫硬提示，一种叫软提示。硬提示就是说你给它这个各种端口，就像今天早上几个报告人讲的一样，就是说你给他语言命令，他去做事情。但是还有一种就是软提示，也就是说你给他一个向量，你可以来调这个向量，通过少量的训练集。所以这就是软提示，我这2种都会展示一下。所以在这个过程中呢，你可以用各种各样的提示方法，我会讲到，比如说怎么去做这种输入的这种改变，怎么去提供模板，怎么去提供这种所谓适应层等等的。那么有了这个提示学习呢，机器学习真正做了我觉得一个根本性的改变。那过去拼的就是3大的样东西：大数据、大模型、大算力。但是有了提示学习呢，我们可以用小数据做很多问题。这个模型呢，你是建立在大模型上，但是你需要训练的部分可以是很小，所以它是个混合模型。另外呢，在这种情况下，你可以用很小的算力做很多的事情。也就是说，这个就是对这种比如我们学术的实验室或者医院呢，没有太多计算资源的人，那么就非常友好。那么首先我讲这个这个 ChatGPT， 这个大家都很熟悉了哈。那么这个过程呢，实际上是通过这种GTP 这个预学习的模型，然后核心的一点就是通过这个所谓这个模型的对接，让它实现社会化。这个昨天已经很多报告提到这个事情。那么这里头由于这个过程呢，就产生了一种推理能力，这就是智能的涌现哈。我们在做这个过程中发现大量的例子，它确实有智能涌现。我今天会讲一点。那一般人研究这个 ChatGPT 呢，主要是把它作为一个对话工具，或者是个知识查询工具，就是说是一个知识库。当然，我们更关心是进一步的这个方向，也就是说知识图谱。另外一点就是它的推理能力。那么首先看呢，这个 ChatGPT 作为一个知识图谱，它因为是在大量的文本上训练的，比如说生物这个相关的这种文献，包括这种就是说 archive 上的文献 ，PMC 或者是 PubMed 这种摘要的这种内容哈，它里头有很多讲生物的这种内容。那么我们认为就是说，通过这种对广谱的文本的压缩哈，它本身就成为一个知识图谱。那么我们看说这个知识图谱从科学角度来说，我们能不能研究这个问题？当然，首先面临的问题就是说，它有很多的幻觉。其实幻觉做计算来说不算什么，因为这个就是所谓叫做这个 false positive， 因为我们预测的时候就会出现这种情况，所以这不是什么问题，只是我们要用科学的方法来研究它，来量化它，来控制它。那么我们做这个问题呢，就是说是一个真正有这种所谓叫 ground truth 的问题，就是说基因 A 和基因 B 它们到底有什么样的关系？那么这个时候呢，就是说我们怎么设计好的这种提示来做这个问题？那这个 ground truth 背后呢，就是这个 KAG 这个数据库哈，因为它对这种基因的关系做了这种系统整理，你可以认为说那里的关系就是这个生物学的真实。然后我们做的方法也是用严格机器学习的方法来做的，也就是说我们有这些训练集，比如说200对这个基因之间有这种比如说有调控的，有激活的关系，有抑制的关系，有磷酸化的关系。然后我们有这个检验集，然后有测试集，所以完全按机器学习的方法来做。这个模型我们用这个ChatGPT 的这个就是API 来做，就3.5的版本。那么当然这个问题你可以直接问他哈，就是说你比如说基因 A 跟基因 B 到底是什么样的关系？不过呢，你一般需要给他一些输出的控制，因为这个 ChatGPT 吧，它是个话痨，你不控制它，它就乌泱乌泱的讲啊，所以你就说，哎，你就给4种答案，就是 是这种激活、抑制、磷酸化，还有说没有信息，也不需要给它不需要提供其他信息，不需要解释。然后这样呢，我们便于来整理这个结果。那么我们可以呢，就是设计这种提示。当然，我们用一些大家都用的技巧先开始哈，比如说这种角色定义。我们这里就说as a computational biologist， 然后你就定义这两个基因的关系。然后你可以用一些知识，这个就是说你产生的知识来做提示。这也是一种技巧。比如说通过 ChatGPT 生成部分的知识，然后你再回去给下一个提示使用。然后你可以指导它各种各样的格式哈。那么这个格式呢，就是说你可以比如说提供这种所谓叫 few shot 这个 prompting 哈，它什么意思呢？就是说我给它几个例子，就是说这个基因EGF 和这个基因 EGFR 它们到底什么关系？然后我们这里给它一个答案，说是activation 就是这个激活关系，这个呢是抑制关系，这是磷酸化的关系。大家可以设想这些 few shot learning 哈，其实是只能起很小的微调作用，它更大的作用是示范作用，就告诉这个 ChatGPT 我们要解决的问题是什么，就是这个呢是更主要的一个问题哈。然后你再去问他，然后你可以告诉他一些知识，就是说这个所谓叫 chain of thoughts， 这个昨天有不少人讲了这个事儿哈，就是说它这个思维链，你可以说这里头解释一下，比如磷酸化到底是什么，然后你把这个知识拷贝在这个地方，然后你就可以来问他了。当然，我们首先在问的过程中发现呢，这个 ChatGPT 是一个格式控，意思说你必须要按照一定的这种格式来问才比较有效。比如 ChatGPT， 因为它是可以回答不同的结果的，你可以问它好多次。那么我们就可以说问它这些例子以后，就说你问 What effect does gene 这个 has on gene 这个，然后你这是第一种提示哈。第二种提示，你就严格按这个你 few shot learning 的格式，就加一个 Q 冒号来问同样的这个问题，然后你就发现说，第一个问的时候，他大部分的时候98次，在100次里98次他都回答说不知道。你第二次问的时候，他95次回答是抑制，其实这就都是回答对了。所以你看，你做这么一点点的调整，他的回答完全不一样。这个就是说明你的格式要和你的 few shot 能对接上。这个现象在用 ChatGPT 里的是非常普遍的。然后呢，你可以做刚才这种比较哈，你比如你什么都不设，你的结果其实也还挺好，就 F1 score 也能到0.5哈。然后你加一些 few shots 呢，加一些这种角色定义，你的结果会好一点。然后你加进一步的解释，你会发现你的 F1 score 变差了，就是说它整体预测反而不好了。但是有一点比较有意思，它的 precision 提高了，也就是说它回答的少了，好多时候他不知道。但他回答的这个内容，只要回答了，他的准确度提高了，也就是说他的幻觉稍微降低了一点。所以这个如果你是想让你的回答降低这个所谓叫 hallucination 的话，你应该给他更多的这种知识和指导。那么这个就是说 prompts 这个东西是不是能够来做一些事情哈？那我们想说这个ChatGPT 这些提示，它就是所谓叫硬提示，它就是语言，语言本身你不能够改，但是你那个提示的组成你是可以改的。那么我们就想说能不能做这种提示，所以我们就做了这么一件事情。这个还真就是我们可能是第一个这么做的哈。那么我们先在这个训练集上就有200对，我们就给一些这个提示，让这200对都去跑的结果。当然我们就用这个 ChatGPT 3.5来跑，然后这200个的这个基因关系呢，我们整理下来就可以得到 precision recall F1 score， 这些都得到，还得到一些错误的例子。然后我们再把这个提示稍微调一调，都是手工调，然后我们再做一遍这200对，然后又得到这些。比如说我们做5次， 然后我们这5次的这个提示呢，和它的结果就给 ChatGPT 4，然后让它来基于这5次提示的结果给我们新的提示。这个呢，就是在做这儿的时候，我们用3.5，因为这个得做好多次啊。这个是等于$2，你可以做这个100万个 token。这个 GPT-4呢，差不多要近20倍的价钱，所以我们在这儿呢效果好一点，但是做的少一点，就是说整体我们节省点钱嘛。说白了，你其实整体都可以用 GPT-4来做这个事儿。所以我们这种做法是把这个所谓硬的这种提示变成可以调整的软提示，但是和后面我讲的软提示是很不一样的。那么这个过程中呢，你会发现就是说，在训练集上，我们这个东西就在不断的迭代中它产生新提示，我们再给它送回这个训练集上再去做，然后每次呢就是把好的提示拿出来，这样不断优化。不断优化之后呢，你会发现它产生的这些新提示它的结果是就是说开始的时候就有提高，那后来呢又在震荡。你比如开始0.333，然后一点点在涨，涨到最好的时候到 F1 score 到0.53。但这个呢是训练集上，我们在这个测试集上同样做，就是这个检验集上同样做这个事情。就 validation set 上，因为它是独立的嘛，然后我们做这个事情以后，就说在第3个迭代里头，它达到最好的结果，我们把这个结果拿来，然后我们在这个独立测试集上再去看它，发现它确实这个整个的 performance 就是全面飙升。也就是说，通过这种东西呢，它真正能把提示给优化出来。这个吧，其实是体现出 ChatGPT 的智能涌现，也就是说，它达到了这个反思的能力，能够看到就是说这个过程，然后就思考自己这个是不是达到最好了。那么我们看它到底改了什么东西就非常有意思。你会发现它这个改的东西非常少。在这一点上，我们刚才讲的是 as a computational biologist， 它变成了 as a molecular biologist specializing in gene interaction， 就做的就是说更加就是对应这个问题了。然后后面改了一点，就是说这个比如说 activation inhibition， 它加了一个括弧，他说 gene 1 activates gene 2， 这个东西好像没有什么意义但是呢，它确实把这个格式定义的更清楚了。所以这些细小的这种调整，使得它的这个整体的 performance 大为提高。那么另外一点，我们 ChatGPT 呢，实际上可以不光做2个基因这个关系，我们可以用那个 chain of cells， 就是说做就是说一个基因的 chain， 比如说基因 A 到基因 B， 它可能中间通过 C 啊 D 啊才到 B， 我们可以通过这种所谓就是说就是思维链的模式，最终就把整体的这个网络呢也都可能建出来。所以这个它真正可以构建比较大的知识图谱。那么我下面讲的这个呢，就是所谓 SAM 这个基础模型那么 SAM 基础模型这个就是说是Meta 也就几个月以前推出来的。然后它这里头呢是有这个图像的这种encoder。然后后面呢，这个它有这种 decoder 然后你 decoder 你可以就是说直接给它提示，所以它本身就有很多提示界面。然后我们也做一些这种图像问题，比如我们做的一件事情就是做这种就是文献中生物的这种路径图的理解，所以我们马上就拿这个 SAM 去做了，你发现它的结果就是非常好，比我们以前用这些其他的方式RetinaNet 或者是别的方式要好多了。也就是说，它在 zero shot 的时候就能把这个这些比如说基因把箭头这些线都能给划分的比较好。然后我们就用它划分的这些组成然后再做一些这种下游的，比如说它每一个模块，我们用 ResNet， 然后来预测它到底是文本还是箭头还是那个叫 T bar 然后来理解这张生物路径图。所以这个就是 zero shot 的一个例子。当然呢，我们在其他的应用中发现 zero shot 不一定够， 那么这个例子就是说，我们做这个电竞的一个图像。电竞呢，这里头它实际上是有这些灰度的这种图哈。然后呢，其实这里头它代表的是蛋白，然后你可以做这种 ground truth 的这种 label， 然后来做这种机器学习的模型哈。那我们讲说，能不能用 SAM 来做这件事情？然后我们这里头有 training data 大概400多个 ，testing data 有67个，然后我们就拿来应用。这么应用呢，当然是也有这种标准了，这个就用 dice score， 也就是说这个人标定的，但人标定的它就是一个圆哈，其实蛋白它不是真的就是一个圆，但近似成一个圆，然后和这个就是说我们用 SAM 输出的结果来做比较，算这个 dice score。那么理想中如果是1的话，就是说完全一样；0的话就是完全不对哈。那么我们直接用呢，就发现它结果还可以，就能达到差不多0.5的程度。然后我们仔细看呢，就是说一些简单的例子哈，它做的就非常好，就是说能够把这个能划分的，就是说非常清楚。但是呢，有些难的例子，它实际上是划分不出来，就因为灰度图呢，这个信噪比不够好。所以我们就是想说，这个到底能够做什么事情哈？那第一点，我们就做了这个所谓叫第3代的这种，刚才讲这种所谓叫做 objective 这个 engineering， 就是说我们能不能来 fine tune 这个模型？其实我们试了很多 fine tune 的模型，在各个地方 fine tune， 我今天就不讲那些，我们就讲的说，就是在这个 mask decoder 这个层来 fine tune， 其他地方都给它固定下来，然后这个结果就有所改进，就比0.5多一点。但是呢，你会发现这个结果呢，就不是特别好，就特别在语义上哈。你看它得到这些麻麻点点的，你算那个 dice score 呢，就是它的目标函数还是挺好，但是呢，它整体给你的语义并不特别好。然后我们就做了3种提示方法。第一种提示方法，我们就说，哎，我们能不能外加一个这种就是 adapter？ 那么我们一般图像处理的时候，你可以加滤镜做这种处理，就做直接的处理。我们觉得我们也试过滤镜，但滤镜效果不太好，因为滤镜本身不可调，所以我们就加一个可调的滤镜。然后呢，这样呢就把一个这种灰度图变成了一个 RGB 的彩图，这就是 SAM 它想要的输入。然后在这个过程中呢，我们也是来这个优化它的这个结果。但是做的过程中，所以是端到端的，就是最终呢，SAM 这块呢它是不动的，所以这个提示工程的本质就是说，它基础模型你不动它，它的构架不动，它的权重不动，你只是在上面加减或者输入上做变化。那么我们这里呢，只是给它加了一个 adapter 一层，而且是非常简单的，就2层 UNet。然后这个过程做下来之后呢，哎，结果就好很多，而且这个还产生了这个图哈，这个就提示后的这个图像，它就变成那种彩图了。其实这个彩图本身很有用，因为好多人做人工标签的时候，基于灰度图，它不见得看得很准，彩图就能帮他看得很准。当然这里也有点问题，你比如下面这个图哈，它这个实际上是这个污染它不太能够区分出这是污染。然后我们就做另一种这种提示，这个提示呢就是用的比较多的一种软提示，就是在这个向量上加一层。当然了，这个向量本身它是 RGB 这个3层的，你不太能加第4层，或者这个图像本身你也不能变得更大。但是我们可以在里头加，也就是说，在这个经过 convolution layer 以后的这个层里头，我们加了一层提示层，然后我们就优化那个提示层，然后把这个提示层就是对这个任务里头，它不断的用少数训练这个提示层，其他的什么都不动。哎，这样做下来的结果就好很多，它就一下能够到0.7几哈，而且它这个污染呢部分的解决了。然后我们做第3种的这种提示呢，是在这个 encoder 这个里面做提示，这个也是基于别人做的工作哈，就是说有人也是在这个 encoder 上做一些东西，我们也就是在 encoder 加一个 adapter， 也就是在 transformer 里头就加一层简单的这个 adapter， 然后呢，在上面去这个学习哈。通过这个呢，你会发现呢，要到0.8级，而且那个污染呢就处理得非常好，所以就是在这个 encoder 你看呢，它确实就是达到最好的结果。那么可以比较，就是说它在最原始的这个到 fine tuning， 然后你看到这种加个 adapter， 加上这个所谓前缀，再加上 encoder， 这里你看到它结果确实越来越好。当然了，也有不同代价。你在后面呢，因为你学习的参量要多一点，所以你需要的内存要大一点。但是新一代的 GPU 40兆这个显存并不是问题。当然，这里另外一点就是说，你那个大模型和小模型哈，我们也看了，就是说你在原始模型上，这个 SAM 它有2个，就是说所谓 huge 就是更大的，这个 big 是稍微小一点的模型。那么你会发现 huge 跟 big 呢差不多。到 fine tune model 实际上它不能做真正 huge 的这个 model， 因为它参量调太多。然后你到这个后面呢，你会发现有时候 huge 好，有时候 big 好。所以这里头呢，可能就需要去真正去试才知道，不见得永远是模型越大结果越好。然后我们也真正想做这种 few shots 就是说你的训练样本是在10个以下哈。那么我们从400多开始，一直到0就是说我们不动。你会发现呢，在这个 fine tuning 这个结果下哈，它的这个 performance 呢就差不多。就是一说你 fine tuning， 其实对它的模型几乎没有太大改变，因为你的数据太少。prompt based learning 呢，你可以发现它也这个 performance 有一定下降，尤其是 head prompting 的时候，你数据少的时候，你会发现它会下降。但是你即使数据到了这个只有5个训练样本的时候，你还是比 fine tuning 好。然后另外呢，你加前缀在 encoder 做 prompting 的时候，它这个下降呢不是很多。也就是说，你只要用非常少的例子，10个以下的例子，它就能做这件事情。然后另外呢，这个 prompt learning 可以在很多地方做哈。我们比如比较了这种所谓 encoder 和这个前缀的这种提示，你会发现就是说，如果你所有都调，它也不见得是最好的。你会发现在这个尾巴上调8层啊，它这个结果就是最好的。前面调其实也挺好，但是呢，最好的是在尾巴这8层上调。这个当然是我们的应用，不同应用可能在不同地方去调这个 prompt， 还是结果不一样的。所以我今天就讲了这个2个这种所谓基础模型，这个 SAM 和 ChatGPT 哈，你会发现它在那个各种生物啊、医学的问题上都是可能够用的比较好的。然后这个 ChatGPT 本身呢，你发现它就是一个有效的知识图谱，你可以挖掘各种东西。然后这个我们呢也做了一个就属于这个把提示自我调整的一个方式。另外一点就是说 SAM 呢，在很多应用中你可以直接用，结果就挺好。然后你当然可以在不同问题中，你可以给它适应哈。比如我们现在也做医学图像，像 CT 啊、核磁共振，那可能就调整的不一样。然后另外呢，就是说这各种各样的这种提示，我介绍了这种所谓加一个这种 adapter， 或者加一个前缀，或者在 decoder 上去做，就这种都是可以做软提示的这种方式，也许对大家有些启发哈。那么我们做的过程中呢，有一些体会跟大家分享一下，就是这个 ChatGPT 本身它确实是个非常好的模型，我们跟别的模型比，那这个 ChatGPT 的整体 performance 还是一骑绝尘的，别人比不了。但是呢 ChatGPT 本身不太稳定，你比如说它前一段时间可以连互联网了，我们发现那个我们做那个用 ChatGPT 编程的时候，它的效果反而差了。然后另外有人这个做了这个评估，比如他把3月份的和6月份的就今年的这个比较，那么它的推理能力在6月份的这个 ChatGPT 其实是有所下降的。这个就让我们觉得昨天这个黄学东院士讲的这个模式哈，可能需要用更广的这种模型去做这种3个臭皮匠的这些事情我觉得在学术上可能也要做这件事情。然后呢，这个提示呢，数据虽然小，但是也是很要求很高的，你不能随便拿几个小数据，你选的小数据必须有代表性，不能是特别极端的数据，不然的结果也不太好。另外，对这个所谓的结果的评估，我觉得在提示工程上，这可能需要比较多的去做，因为 如果你基于小数据评估，可能会高估你的这个能力。还有一点就是说，提示工程，它也有缺陷。我们发现它的缺陷就是说，它的泛化能力可能不如一些普通机器学习强。你比如说，当2个任务很接近的时候，那么我们一般的机器学习，比如说你人脸识别或者是卡通片的人脸识别，它可能用正常人脸的识别也能做卡通人脸识别，但是到提示工程中，当任务即使很接近，可能不能达到这个。所以它任何的这个事情，我们机器学习里有个叫 no free lunch 的这个规则哈，就是你不可能只有这个收益没有代价。当然，我们也在探索这个提示工程做别的事情。我们发现提示工程这个就是 ChatGPT 上本身就是一个很好的推理机。我们比如说用蛋白的序列，就用 ChatGPT 来做 encoding， 然后做很多下游的事情，都非常结果惊人的好。当然，我们做的数据还不够多啊，今天就不报告了。包括这个化学这种分子，你用 SMILE 的格式来做，包括 RNA， 所以这个就是作为一个推理的能力，后面的潜力是非常大的。好，今天我就讲这些。我们这是参与的这个一些人哈，就是 Sam 这个工作，主要是何飞牵头做的。ChatGPT 主要是陈一博，他们2个都是我们组的博士生。然后我们有很多合作者包括那个下一位那个嘉宾那个陈明老师这个工作是 NIH 支持的。好，谢谢大家。对对。对对，是这样，对。对。对，这当然也是一种途径，但是呢，你逃100次，它逃的内容是差不多的，所以你并不是能够就是说覆盖很多，就是说这个还是。对，这个是可以探讨的。就是说，我们现在也在用这个，比如说 genetic algorithm 啊什么之类的去做这种尝试优化哈。甚至我们想优化的已经超越语言，就是不见得是人可以读得懂的语言，我们可以让机器读得懂，人不用读得懂就可以。所以我们都在做这种探讨，但是这些结果还没有特别理想。对，是这样的，是这样的。我觉得这个是提示工程可以做这件事情，就是说你可以把这个所谓叫 position 定的阈值很高很高，就意思说他很少说话，说的话就是靠谱的。对，好，谢谢。好。
您好，那个徐教授，就想请问一下，就是对于 life science 这个领域我不是特别了解，但是之前读的话，就首先我也是非常看好 Sam 这个模型的，然后之前 Meta 发布出来之后，就是怎么说cool down那段时间，我还是觉得就其实大家低估了它的意义。那今天非常高兴看到您探讨这个对于 drug discovery 非常大的影响。那之前我读的 paper 就是说，像那个 AlphaFold 那样子的这种那个模型，它在那个 drug discovery 上面有很大的应用。那今天从图像上面，其实我想了解一下，目前 drug discovery 这边的 bottleneck 是在哪一部分？然后就是为什么这个图像上的这个 segment everything 可以很好的去帮助大家去那个怎么说去找到这个新药，或者去做就提升它的一个either recall or precision， 就是说为什么是从图像上，而不是说是从它的那个基因的一个那个怎么说原理上面？就这个我有点专业上面不太清楚，想请教一下。
对这个吧，就是说，制药是一个非常长的一个研发这个链哈，就是说，它最终一个药最终能被美国药监局通过，一般都是1个billion dollar 的这种级别，所以呢，这个真正的瓶颈并不是现在 AI 这些方法，所以我觉得制药这个领域 AI 为王还是差得非常远的。为什么呢？因为 AI 做的事情就是前面这个工作，就是说怎么能够把这个药物的就所谓筛选它一些靶点药物的可能性，这方面 AI 确实大幅的这个提升了。但是这个呢，在整个制药的环节中占的其实是一小块，后面有比如说动物实验、人的实验呐，包括它的这种side effects 这种研究哈，所以那些是至少在成本上是大头，而这块并没有有所突破。然后另外一点，你刚刚讲的图像哈，这个制药理论上讲其实一个多模态的问题，你可以用这种各种各样的，比如说蛋白的这种序列结构，蛋白的多组学，包括这个后面这单细胞啊，好多医学啊、图像啊都可以用。所以呢，真正做药过程中，它确实是整体的这个使用。当然，我们是做学术，是在做基础研究，不是做这种所谓 close loop 这个做公司哈。所以我们只是在一个点上做一些创新。
好的，好的，多谢。
好，那我们就鉴于时间关系，我们就往下走哈。然后这个我们第二位演讲嘉宾呢是陈薇老师，她是一位从学术界走向产业界的这个杰出女性代表，也是计算机视觉领域的知名专家。这个陈薇老师毕业于清华，然后博士呢是毕业于卡内基梅隆大学，期间呢也领导建立了该校的计算科技中心，之后又去了纽约州立大学Albany 分校任教，直到2018年加入微软。他不仅拥有美国专利商标局授予的30多项专利，而且成果呢也广泛应用在 Bing、OpenAI 和这种 GitHub Copilot 等产品中，所以在这个信息技术中，真正是做了很大的贡献。那么他今天讲的这个主题是 AI for Microscope Image Analysis 3.0，让我们掌声有请陈明老师。
谢谢徐老师，也谢谢大会组织者，尤其是很多幕后的工作者，很多细节周到的帮助。因为我今天讲的东西呢，有很多算法，有些词汇呢，好像也只在那个英文的文章里看过，所以呢，我中文、英文相切不是很规范，我就用英文讲了哈，也比较规范一点。Yeah, so the reason I want to talk about microscopy image analysis and the so-called 3.0, I also want to show that, as you heard from a lot of these talks and conversations, on the one hand, we are all making effort to advance AI. Meanwhile, I think all of us are also trying to adapt to the advances in AI so that we stay at the cutting edge and also our work stay relevant, right? Because the field is advancing so quickly and at a scale that's quite unprecedented with a previous technology. So what's the big deal about microscopy image analysis? Why do I call attention to this? So let me show an example. Hopefully play. So when I first saw this data, I was fascinated. That was years ago, and some of you are probably familiar, have seen something similar data. These are mouse muscle stem cells, live stem cells in a petri dish. It's supposed to repeat, but it stopped. So it's moving around, so it's in vitro, and some of them are dividing, some are dying, some are differentiating. And when stem cells differentiate, that's actually the power of stem cell, right? That's why we do stem cell analysis, is that so that they can do tissue engineering to repair tissues that are diseased or injured. And since these kind of experiments can go on for days, maybe more than a week, and this is actually a sequence of images taken every 5 minutes in this case, and for some other cells, it's taken every minute. So you can imagine if that goes on for days or more than a week, there's a lot of data. It's impossible for a human to maybe go back. Maybe if I went back, then you can come back. Okay, it will play again. It's impossible to a human to really keep track of each individual cell, which is actually necessary for stem cell engineering, manufacturing analysis. And so currently, what the scientists do is that they take a look at the local region and count the number of cells. They can't really track them. So what they need is actually what you see in this other one. You want to kind of identify, each individual cell and keep track of them. The different colors denote different identities, and a little, kind of tail are the recent trajectory of the cell movement. We actually want to keep track of that from the beginning to the end of the experiment, to construct the cell lineage. So here we can't show all of that because that's really difficult to see. So it only show the recent history. And you can imagine how challenging this task is, right? So I was fascinated by this kind of challenge and also the very meaningful work, right, for stem cell therapy, and started working on this. And this is, kind of, see the videos. Always a challenge. Let's see if it plays here. Yeah, this is a zoom into a local area, right? This is in plane view of different cell identity, how they move around. That's, the vertical axis is time axis, so you see how the trajectory is being tracked. And, later on you also see how when, the trajectory branch, that's a cell division, right, to analyze that. So in order to, bring more attention to this field, me and my collaborators started in 2016. We proposed a workshop to CVPR, the conference, and we were very grateful. At the first time, it got accepted as a half-day workshop. And there was a lot of exciting talks, a lot of interest with great attendance. And ever since that, we have been able to get this workshop accepted and organized at CVPR for 8 years already, till last June we had the last one this year. And through this process, we also observed a lot of development, and also kind of the field is also kind of shifting its focus because of the the advances in AI, and everyone is trying to kind of stay on top of the most exciting topic and also the latest approach. So I did something really trivial just to show that this was taken all the talk titles from invited speakers and accepted papers back in 2016. So see that segmentation was all the rage, right? People are excited about the problem, and there is learning. But even the keynote at that workshop was on model-based approach. That's even till 2016. And there's people are exploring learning and networks, and that definitely changed very quickly. After that, this one was from 2022. So see that definitely deep learning, right? People are all employing that kind of approach. Segmentation is still a very important topic, and you see more and more attention to pathology. Digital pathology used to be a field that's really difficult to break into from technical perspective. Now there's more acceptance, more data available, and also more investigation. And another thing that really emerged over the past few years, until last year, is that multimodal omics, has been starting to get attention, with fusing different modalities, integration of that, and a lot of interest and investigation there. And as we all know, right, I think it's actually over the years accumulation, but last year somehow there seemed to be a lot of quite big breakthrough, right, in AI, both with SAM, like Professor Xu was mentioning, and also with language models. So then this year, when we had a workshop, there's further development. You see that the approach, instead of just mentioning learning deeply, even in myself, right, with my collaborators, at first we were even trying to innovate along network architecture, and by then we start to accept that let's just use foundation models. They are good enough, and focus our attention on really making a model work for specific applications, right, so that they actually can be getting closer to real-world application. So the self-supervised transfer learning, etc., was getting a lot of attention this year, and with the segmentation pathology, etc., still getting a lot of investigation. One other thing we noticed is also this year, because there's also a lot of development in the microscopy technology. Image resolution has been increasing, and also I don't pretend to understand details like droplet-based technology for doing experiments and acquiring data has also advanced a lot. So this year, several of the invited talks are on single-cell analysis. Apparently now you can actually really study each single cell to really get further, deeper understanding of life, right, of ourselves, and a lot of related technology, leveraging AI, has also been forming. So similar to this, with the same progression, I also noticed, myself and our collaborators, our research has also been kind of, adjusting to what is the latest and, most exciting. So from cell tracking, I also start to, with my collaborators, start to pay more attention to pathology image analysis. And like we're showing here at first, we also try to attempt to do some network architecture innovation. Later on, our attention has been, more on the domain adaptation. Domain adaptation, I think, a lot of the audience are probably, have more expertise than I do, is that you have a source domain, and with that, you have a sufficient, hopefully, training data to do, really good gradient-based learning. Meanwhile, there's always going to be new domain coming up, right? There's a domain shift, and also with new classes emerging. And we don't always have the luxury to collect, additional sufficient training set, because for biomedical images, as we all know, right, to get high quality annotation needs some domain expertise. So it's even more expensive than other kind of data set curation. So here we have been studying this unsupervised domain adaptation for quite a few years. Essentially, the goal is to alleviate burden, right, of very expensive data annotation. And unsupervised meaning that in the target domain, I may have very, very few quote-unquote, support data, meaning very few data annotated with 5 or 10 examples, something like that. But assuming in a source domain, I have adequate annotation that I can use that, right, to adapt to the target domain. And here, the challenge is, as you can see in this example, is that there's domain shift. Typically, for the target domain, it will be of something different, right? It all looks like pathology image, but maybe of a different, organ. So there's domain shift. And then the label sets, there may be some classes in common, but there will also be, new classes that are not covered in the source domain. So how you adapt the learning from the source, right, to the target, that's the challenge here. We have been studying this for a few years, and we saw that challenges also mean opportunity, right? So one thing, as we study, we start to realize that definitely current gradient-based optimization typically, right, needs sufficient data to guide the update steps. And then if there's more data or big domain shift, then the update can be noisy or lead to overfit. But the opportunities that particularly looking at a lot of related recent work, we realized that we can actually instead of, because we studied different approaches, now we are thinking that the adaptation will be more about optimization process. Can we, transfer the optimization trajectory from the source domain to the target domain? And also one thing that's, giving us a lot of insight that we want to leverage here is that for the stochastic gradients, the optimization tends to be low rank, and we want to exploit that, right, to do this from source to target adaptation or, distillation. So here is our idea, is to essentially exploit the low-rank nature of the gradient space and distill the optimization trajectory from the source, right, the teacher, to the target, the student, and in that way provide external guidance, right, for the optimization in the target domain. This work just got accepted at ICCV this year, so it will be published. It's already on archive, will be published next month, presented at ICCV. So it's the first time I'm talking about this, kind of a preview. This is the overall design, from the source domain and to the target domain. As you can see, there's something in common, and also, quite a domain shift and new classes. And the distillation, I'll talk a little bit into details. Here, overall, we call that dual stream distillation. One part of the stream is this cross-domain, right, from source to target, and cross-class distillation, because there will be new, novel additional classes. And here the steps, right, sounds, a lot of terminology. Really, it's about, exploiting the low-rank nature of the stochastic, gradient descent, so that, we distill the learning from the source to the target. And anchor classes, meaning, right, what's in the source domain. Those are, classes with adequate train set. So to exploit the low rank nature, we do singular value decomposition to identify the principal eigenspace in the source domain, and then do this low rank matrix approximation to select the top significant vectors, and then construct the principal subspace so that we can project the gradients onto the subspace and then minimize the discrepancy between the projected gradients. So that's the gist of the approach. There's definitely more detail in the paper and also with the source code, open source. And another part of the dual stream distillation is this so-called self-distillation. We actually debated about the name, whether to call it historical or temporal. This historical here means what happened in the past. And the reason is that even with the previous approach, if the target domain bears quite a bit of a similarity to the source domain, the approach generalizes well. If not, it still doesn't work out that well. So how to make this approach generalize better? We also learn from related work that typically there's some connection between a very flat minimum and the generalizability. So we learn from that and try to kind of enforce our gradient steps to calibrate that to smooth this optimization. Hopefully that will generalize better. And the steps here, that's why we call that historical self-distillation. We took the past gradients every so often in that optimization process to identify, again, low-dimensional substates. Try to, I guess, low-dimensional is something that, more stable and we can understand better. So we, try to exploit that property to get, the principal gradient distribution of the local minimum. And then we project the current gradients onto this, the principal subspace to hopefully, smooth out the sharp and the noisy signal. And then we treat this projected gradient as a residual. So when we do the optimization, we actually sum up the original and the so-called rectified gradients to do the, the subsequent optimization step. So this is the other half of the dual stream distillation. And then we'll take a look at the evaluation. We look at quite a number of data sets. Part of that was because of the review process. Reviewers, kind of like the result, but they are always skeptical. So we did a lot of experiments to show that it definitely applies to a lot of the data sets we can find. So this problem is about cancer tissue phenotyping. So the source domain has 5 classes. The target domain has 6 classes, and there are only 2 classes in common. So there's 4 novel classes, and it's a different domain. And the overall task is about classification. And here, the 5-shot setting is assuming the target class have 5 support. Essentially, 5 data samples are labeled, and the 10-shot is 10 data samples are labeled. Overall, quite small labeled data set. The rest of the data sets are unlabeled, and the data are unlabeled. So here, the color, the numbers that are colored in brown are previous best results from different approaches, all related work. And the last row is the numbers in bold from our approach. It is a dual stream distillation. And you can see that overall, I think a lot of them is quite a significant lift, for 4 or 5%, on both the mean accuracy and also the mean FM metric. The metrics with the asterisks, they represent the metric that's calculated only on the novel classes, the 4 classes. And the rest are average across all the classes, including the classes in common. So this is one data set. And then we also take a look at the optimization trajectory. Remember, we are trying, overall, what is really happening here is to use a source domain optimization trajectory to kind of regulate the target domain optimization trajectory, right? Tries to do the adaptation there. So here, what's in the green color shows a quote-unquote, baseline optimization trajectory without this distillation of from source to target. And you can see that, first of all, it's kind of trapped in a local minima, and also there's a lot of sharp kind of oscillation, right? Not a very elegant, smooth, right, optimization. And then the one in blue color, first of all, it did reach the the right minima, the global within this context, and also relatively fewer sharp oscillation. So it's a bit better performing without the distillation. This other one is showing the quote-unquote flatness, right? We were saying that for the the better generalization, the local minima should be the minima should be relatively flat. So here the vertical axis shows the accuracy gap, and the horizontal axis shows the parameter perturbation. So the good quality optimization approach is that the oscillation should be small, right? Otherwise, it's very sensitive to different parameters. And you can see that the blue color come from our approach, and in general, right, it's a gentler slope, less sharp oscillation, in the performance gap, with the parameter perturbation compared to the baseline. So relatively better behavior. And then we show more quantitative evaluation. Like what I said, whenever nowadays we develop something, people always say, well, you cherry pick, right? On some tasks, it seems to do well. What about other tasks? So this is a nuclei instance segmentation classification task, meaning that you want to kind of get a contour of the nuclei and also classify, right? Recognize what that is. And here again, we evaluated with two settings, 5-shot and 10-shot, 5 or 10 support samples in the target domain. And also one metric is F1, one other one is called panoptic quality. Basically, it's a combination between for segmentation metric, the intersection over union, and also classification metric, with false positive, false negative, etc. So here again, the numbers in brown indicate the best previous performance, and the numbers in bold on the last row, the numbers from our approach. Again, overall, it's quite a nice lift, compared to previous approaches that overall the approach still can apply. And we also evaluated on this other data set, that's skin lesion. I forgot to mention in the previous one, I think there was 2 classes in the source domain, 8 classes in the target domain. So there's 6 new classes. In skin lesion, it's a different kind of task. The source domain are coarse classification, so 2 high-level classes. And target domain was, I think, 6 or 7, I forget, finer level classes. So that means there's actually no overlap in the classes, completely novel task. And also, again, with the same kind of notation that our approach performs quite a lot better than all the previous approaches. So it's quite well behaved in terms of the applicability of the approach. And then we also did this ablation, right? People say, you talk about fancy design dual stream. What does each one do? Do they really contribute anything to the overall task? So here at the top row shows the full framework, right? The result, and then we kind of remove each component to see if it matters. And it does seem to matter, right, to different degrees. It does depend a little bit on the task, particularly the skin lesion data set is there's a lot of class imbalance, so the behavior tends to be a bit different. But overall, you can still see that, with the removing each part of the overall architecture does, reduce the performance. So it seems like, each component is still necessary in the design. And then here, we got challenged by the reviewers. They say, you show on microscopy image, but when people, to make it worthy of publication, what if I'm interested in other kind of data? So here we evaluated that on 3 very different tasks. One is a radiology imaging for pneumonia screening. One is, the fundus image, which is essentially, the image of the back of the eye to diagnose diabetic retinopathy. And the third one is something totally different, not in biomedical imaging. It's the office home data set to evaluate, from the artist kind of domain, rendering domain, to real world data domain to see if the approach still works. So again, here we only did F1 metric given I think at the time the time pressure compared to other approaches and the baseline. The overall performance boost still applies, and also quite a big lift for the natural image, of his home data set. So overall, it does really well. And here, just show some pretty pictures. Qualitative evaluation, because numbers, sometimes what do they really mean, particularly if it's a 1 or 2% improvement, does that really mean anything? So here, just for some intuition, this is on the nuclei segmentation and the classification task, because there's more things to see than just classification. So on the left is the data set in the target domain. Here's a ground truth, right, of nuclei segmentation. Also, different colors denote different classes. And the approach is the third column, and then with other kind of SOTA approaches from recent years. And you can see overall the behavior, right, even on a qualitative, intuitive level, also it's much nicer that overall the both segmentation and also classification, right, is much closer to the ground truth. It's the different classes in these data sets. So I think just to conclude, in the interest of time, is that from our experience for this supervised domain adaptation, instead of just looking at the labels and the data itself, we pay more attention to the optimization trajectory to more do adaptation directly on the optimization itself, to distill from the source domain to the target domain with a dual stream approach, right? One is more the domain cross class. Another part is from the self distillation, but more looking at the flat local minimum approach, right? Using the path gradients to project to the low rank subspace. And the paper is already posted on arXiv, so if you're interested, and if you attend ICCV, please stop by our talk and our poster. And with that, I will conclude in case there are any questions. Thank you for your attention.
好，看大家有什么问题 ？OK， 呀、yeah.
Yeah. Let me go to the slide. Slide, I think number 17. Yeah, that's the same task. Yeah, I showed. Yeah, same task. This is more the quantitative evaluation, and then that's the qualitative one. Yeah, these are all the previous approaches that they also tested on this data set. It provides pretty big lift across all the metrics, both for the F1 is more the classification, and then the panoptic quality is about both segmentation and the classification.
Okay, I have a question. Yeah, so your method lifted the performance a lot, but if you look at the absolute numbers in terms of F1 score, ACC, etc., it seems it's still pretty far from 100%. So what are the challenges in terms of reaching to 100% accuracy for F1 score?
Yeah, it's very tough. So here, actually, I think it's still because of lack of real high quality annotated data. Okay. So here the first one, the sub-only as a baseline, the first row, it's actually if you train just on the novel classes. There are very few label data, so the performance is really poor. And then the second one is trained that across the new and old classes. And you see it's sometimes better, sometimes not even much. It's a really tough task. And then overall, people try to adopt from the source to target. It does somewhat better, but still, yeah, I agree, it's still pretty low. Particularly when you also combine with segmentation, you will see that the F1 does a little bit better than the MPQ, the panoptic quality. With segmentation, there's also the overlap of the contours.
I see.
So that part still suffers. Yeah, definitely. So even in some, from my other part of work that's not related to biomedical imaging, still that high quality, even not high quantity, but high quality train set still makes a big difference.
Okay, thanks.
Basically, But so far we can do with 5 or 10 examples. And yeah, definitely I think with the latest development, with SAM and those approaches, maybe we can also think about a different way. In addition to domain adaptation, can we also augment data through the generative model? Because currently what's really is trying to tackle is that it's really expensive and hard to get high quality human annotation because it needs expertise. But then now can we actually generate data from a few human annotated data set to generate more artificial insights?
Okay, all right,
we
thanks.
are already doing that with typical, definitely with text and also with some kind of images. But then with biomedical, I think it's just a matter of time.
Okay. Any other question? Okay, one more question, yeah.
Yeah. I think the next slide here, we also showed it works for images and radiology or other images. Because fundus imaging is essentially just a digital image of the back of the eye. And like what you said, it's actually very common because the stochastic gradient descent, there's a paper cited, I can show you in our paper in the references. There's a paper actually analyzed that. Stochastic gradient descent, actually it's very low rank. That's why we can use SVD to just get the principal subspace.
好的，让我们再次感谢陈梅老师给我们带来的精彩报告。
It's on archive and the code is also open source.
好，这个 session 的最后一位演讲嘉宾是来自纽约市立大学电子工程系和计算机科学系的特聘教授，田英利老师。他具有多种专业背景，先后学习精密仪器与光电工程学、热物理工程学、电机工程学等多个专业，并在卡内基梅隆大学机器人研究所、IBM Watson 研究中心带领团队多次获奖。2008年，田英利老师加入纽约市立大学，专注利用计算机视觉和机器学习等技术帮助老年人、视障、听障等特殊人群，并当选美国电气电子工程师协会和国际模式识别协会的2会会士。他今天给我们讲的报告是AI-driven Automated Medical Image Analysis。让我们掌声有请田教授。
Thank you, Professor Xu. I saw in our audience we have a gentleman there, so I will still keep the talk in English. Today's talk will focus on medical image analysis. This is only one small part of my research. My main research is about the computer vision, focus on the human behavior analysis, and also apply that to the assistive technology, just like Professor Xu introduced, which include the how to use the computer vision technology to help blind people or other people who has the special needs, such as deaf people for the American Sign Language. Okay, so I will start. Let's see. Okay, so I think for the medical image analysis, I started this research several years ago because of family reason. So here, from the figure, you can see most of the medical images, I think everyone experienced that. If you didn't experience that, you are really lucky, okay? So for the MRI, ultrasound, X-ray, and also CT, PET, mammogram, all this, right? It's involving our daily life. But how can we do it by apply the AI-driven things to really help, I think, both the doctors and also patients to get those kind of, analyze in a more accurate way and also to do more accurate diagnostic. Just as Professor Xu's question to Dr. Chen, is still far from the 100%. I think it will never be 100% because for the different patient situations, all change and it's all progressive. If the AI can really achieve the accuracy for the well-experienced, our well-trained radiologist, our pathologist to that level, then the AI method will be widely used in all the systems. It's already being used in many applications, but for the medical images, it really depends on the accuracy compared to the experienced human, our doctors. My son is a doctor. I discussed this question with him. I asked them, do you think the radiologist will lose their job when the AI is really in that level? He said, no, will never. Do you really trust a machine diagnose your situation? He said, in that case, if AI can do really good job, so the doctors can see more and more patients. And also for now, you see, even for the cancer screen, they only apply to some specific patients. They will not do for everyone. But if the AI can do that, then more people can do the early screen, so we can really reduce the death rate, especially for lung cancer. So I'll start, to say most of the AI-based medical image analysis now concentrate on 4, categories. I put in there. So the first one is the synthesis, mainly includes the image registration or the medical image translation. For example, for those kind of expensive, scans, for example, people how can transfer MRI images to CTs or something like that. Also for the detection, this mainly try to use the images automatically detect those kind of abnormal, regions or tissues, so we can do the further diagnosis. Then people also can do for the segmentation. How do you segment the organs or the abnormal regions from the other tissues? The last one will be diagnosis. That's the real part will help the doctors to make it. Okay, so in this case, since we just started several years ago, so I want to share our studies for 2 topics. One is how can we do the virtual, contrast enhancement. That means without use those kind of, contrast dye, can we do the AI synthesized contrast image? So in that case, for the patients who has the kidney disease or the kidney dysfunctions, can we really help them without doing that, but still get the contrast images? The second one is about the AI-driven automatic cancer diagnosis. I will focus on 2 things. One is the lung cancer, and another one is the kidney cancer. Depends on the time. Okay, I know everyone's hungry now, so I may skip a part of that. Okay, so now let's move to the, the virtual contrast enhancement from CT scans. Here you can see for many diseases, patients will get those kind of, contrast dye to highlight their inner organs. But for some patients with the, the kidney disease, it's really hard. We'll get the really, the serious, the dysfunction for their, for the allergy things, for their, kidney things. And also some doctors may try to reduce the dye, but after you reduce the dyes, they may also reduce the highlights of the organs. Then that will need the repeat, the injection, which will even worse, okay? So in that case, we tried to develop AI methods to see how can we really do the, eliminate the dye, the injection. Here is what we want to do, We generate the idea to say, okay, how can we generate from the CTs, from the non-contrast, from the non-contrast CTs to generate the virtual contrast. Then we compare with those kind of real contrast CTs about that. So here I used 2 different kind of terms. One is a pre-contrast CT. That means for the patients who really get the inject. So just before and after. For the non-one, that's the total is a patient CT without that, just to compare with the virtual CTs. Here in that case, most of the existing method for the virtual contrast CT only focus on MRI images and only focus on the brain image. But however, our the method focus on the abdominal and the pelvic, this part. Compared to the brain, this part will be more challenged because when patients lay on the CT machine, the position is changed and also the inner organs will change. So that will cause the much bigger misalignment between different kind of scans. So in that case, we have to handle the the misalignment and also compare with the brain features. Our inner organs of this part will have much more complex features. So how can we extract that so can get both detailed texture and also the global the alignment well. So here we propose the detail-aware and dual-path contrast enhanced framework. So in that case, we have the non-contrast CTs here. For the global path, we input the whole CT, the whole volume in there as the input. For the local path, we cut the the images to the 4 grids. Then we try to focus on more detailed features. Then we fill them together to get the predicted virtual contrast CTs. Also, I think because the big alignment, doesn't matter how hard we try for the pre-processing, we still have the large misalignment there. So we tried to use the perceptual loss function to handle it, so we can get a better result for that. I want to just to show you for the data set we use total 65 patients for that. It's pretty small data set. I think that's one challenge for the medical image processing compared to the large language model and also computer vision large, just like recently for the segment anything, that's also pretty general model. So also because of patient privacy, they're not that large data set shared for the medical image. I hope someday we can have the big enough data set so we can train the general medical model. Then for each different kind of specific application, we just do the fine tune. So that's I think will happen in future after we remove the patient's private, the identity information. So you can see here in our method, we are not only handle one the contrast phase. We have the pre-contrast CT, then we have the 3 phases of the the highlight. The first one is the arterial. That's just after you inject the dye, we will scan it. Then after a little while, we scan another one, that's a portal phase. And also we have the delayed after several minutes. For each of these phases, different kind of organ will be a highlight. So our method will try to handle all the different kind of phases by the single framework. Okay, here, I just want to show you here, the first row shows you all the non-contrast CTs. The second row shows you the real contrast CTs. The third row is our CTs, the virtual contrast CTs. You can see compared to the ground truth. Pay attention to the 4th row. You can see it's very close to those kind of real contrast CTs. We also tried the cycle guide of the different kind of loss functions and also the contrastive loss. You can see for the main part, some of them cannot be really highlighted. Okay, we also evaluate our method by 2 radiologists in the blind review. That means we send them the different kind of contrast CTs without tell them which one is the real contrast, which one is generated by our method. So you can see why the radiologist 2 like our system much better than the radiologist 1. So we evaluate it in 5 scales: poor, suboptimal, acceptable, good, excellent. So you can see we get the average about the score 3. That means acceptable. But still, there are far way to go. I want to show you some of the, the limitations. Most of the limitations we cannot handle as we create the patchy enhancement. That means for the whole part should be highlighted, but the virtual city only highlight a part of that. Or also for some part, the real city, contrast cities are highlighted, but we miss it. But sometimes it will also generate unnecessary enhancement. So that's the part we really need to, improve that. And just to quickly summarize this part of that, we are the first one to generate the virtual contrast city for the, the abdominal and the pelvic region of that. We are also the first one to use the single framework to handle the multiple contrast phases. For the future work, we want to really do not only for that, axial cities, they have the different kind of, projections. We may also include them. Also, I think for now, if we have more data, how can we use the field data to fine-tune it? That's the active learning and the field shot learning for that. I'm also thinking the basic thing is not only say how similar the virtual city to those kind of real contrast city. We do this kind of contrast mainly want to do the downstream task test. That means how can we really do for the cancer detection or some, abnormal detection. If the virtual city in the downstream task can achieve similar result for the real cities, then I think we finish the task. We don't really need to get really similar of those kind of, image as the real contrast city. Okay, so let's move to the next topic. That's the AI-driven automated diagnosis for, lung nodule detection. I lost my husband for the lung cancer. That's also when we visit the hospital, so many times I built the connection with the doctors. That's why I started this research. Okay, so lung cancer, everyone now is the first killer for the cancer. And also most of the case, when it's diagnosed, it's already the stage 4, so we really want to do something. If we can do the cancer, our nodule detection at the early stage, then what we can do, right? So in most of the existing methods only use the 2D detection networks. Sorry for that. They only use the 2D networks without use the temporal information for that. And some of them just use the 3D detection network, but with not that high enough, sensitivity and specificity. We can simply, understand the sensitivity. You can say simply as the, the precision, okay, the accuracy. The specificity, mainly you can think it's about the level of the false positives. So we want to really combine that. Okay. So in that case, the remaining issue are still miss the detection on small nodules and also with much low specificity. That means we'll generate much more, high false positives. We don't want that to happen because the following up treatment will depend on the detection. If there is no nodule, you say, okay, there's a nodule, then maybe biopsy or those things are really unnecessary. We don't want the patient to suffer that. Also, it's low robustness. That means for different kind of scan machines or different systems, if you train your system on specific data set captured by some model of the CT machines, then if you test your method on other data, then the accuracy will decrease to a lower level. So can AI method help to accurately detect the lung nodule and reduce the false positives? So we tried that. we designed the, the method, we call it the 3D feature parameter network, and then followed by another false positive reduction network. It's really, amazing. For those kind of nodule and tissues, if you only observe them from the, especially for the false positives, only focus on the small region, you cannot see difference. Here, I just want to show you one compare of them. Those are the real nodules, but that one are the, the false positives. But when we really project them by use several slides, use the local image history, then our network can really reduce them dramatically. So in that case, we really can create a very low, very low false positive. Instead of, only use that small data set, we also proposed to use the self-supervised learning to really learn from the larger data set. I think they have the NIH collected the early, lung cancer screening for those kind of cities. Without use any ground truth, we just rotate those kind of images to 90 degree, 90 degree, 90 degree, then come back. Because we rotated them, we know which degree it is. So we just train the method to learn, okay, what's the degree of the image we rotated. Then in that case, we learned the pre-trained model for the feature learning. Then we apply those kind of features to initialize our model, which largely improved the result. Here, I just want to quickly show you some of the visualization results. You can see our method can handle very small nodule, about 3 millimeter, to the larger one, about 30 millimeter. So the whole data set, the maximum, the largest size is about 30 millimeters. Okay, here are the, the more detailed results. We compared it with the state-of-art result. We also tested it based on those kind of, different kind of, you can see here, we used the, FROC, that's a free response receiver operating characteristic method about that. So one of is, that's all based on the false positives. That means for per scan, per CT scan, how many of the false positives we can detect it or are allowed. So you can see our method achieves very high, scores. We also evaluate that with our result, those kind of, different kind of, the reduce of the false positives. You can see it's really doing very well. And here also we tested the robustness across different kind of data set to see how well it will perform. Without any retrain or retune, you can see the performance keeps pretty good. So it's pretty robust. Okay, quick summary about this part. So we focus on really reduce the false positive, and also we did very good. And also the self-supervised pre-trained model also improved the result a lot. Okay, so now we just want to, since this part we did really good, and also we know for the CT scans are projected to different kind of access. Then our next idea, can we don't use those kind of projections, the CT images, but instead of use the CT images, can we really use the the 3D point cloud? Here we tried, you can see here, compared to the CT images here, for the CT point clouds, we have the geometry invariance. You can really do the multi-perspective projection, and also we have the real, world coordinates about that. It can handle irregular shape, but we don't have the grid alignment. But for the 3D point, we couldn't get the texture features. Those are the drawbacks. But we have all other advantages of the CT images. So in that case, we apply the, the point cloud directly, and project it in, I'll skip this because of time. So we propose this framework. We project the 3D point cloud to N wheel samples. In our research, we did the 4 wheels, but we want to do extend it to multiple wheels. So I'll skip the details about that. Here are our result. We did pretty good for get the comparable result with the state of art, but still for the accuracy, it's still lower than the framework we talked before. Mainly, it's like the accuracy for the detection of the very small size of the lung nodules. So the previous framework we talked can handle the small nodules much better. So we will think about how can we really go to the more local features from the 3D point. Okay, so I'll skip that. So we'll quickly go to the diagonals for the kidney and renal mass segmentation and the classification. This one combines the segmentation and the classification. The segmentation means when you give the CT scans, we need to segment the kidney regions and also the nodule regions. After we detect the nodule regions, we want to continue to do the classification for which type of the nodules, because different kind of nodules have the different kind of, the progress. So the doctor needed to do that. So in this kind of things, we have 2 frameworks. For the framework about the 3D segmentation, we have the 3D CT impulse. Then we segment the regions and also the nodule. We crop that small regions. Then we input the small regions, then into that classification network. Then really can separate, classify the subtype about that. Okay, here are our results. You can see for the first table shows you the segmentation results. Our method compared to the state-of-art result, we achieved very good result. The bottom table shows you the subtype classification result on one data set about that. We achieved 80%, more than 80%. So doctor said that's comparable with the human radiologist for that. Okay, here we also try to, how can we improve the result? So we tried the weekly supervised classification. That means for the classification, without really use all the annotation for all the frames. We just use for the nodule part the first slice, and also for the slice with the bigger size, the bigger size, and also the last slice of the nodule. Only use 3 slides. You can see we can improve the result. We can improve the result. The first row shows you without the weekly supervisor training. The second row shows you with the supervisor training. You can compare the numbers. Even with only 3 slides per CT scan, we can largely improve the result. Okay, so I think here are the quick, visualization result. You can see in the orange, the red one, that's the kidney. In the blue ones, that's the, the nodule, the cancer, the nodule. Also quickly summarize it. We developed the framework can handle the segmentation and also the subtype classification, and also by only use several slides for the weekly supervised can largely improve the result. Before I finish it, I just want to quickly summarize our, predict what we needed to do in our future. I think most of people, especially for the large general, the model available, I really think we will have the large general model for medical image processing. And also, as Professor Xu mentioned, the field short learning and also cross different kind of domain will be another trend of that. I think if we couldn't get a good result, I'm still promising at least that means I still can keep my job, can continue doing this direction, right? Thank you very much.
All right. Any questions? Yeah, I have a question. Yeah. So in your case, yeah. So for people have of course a slight variation of our organs, but by and large, one organ has a somewhat standard structure. So I'm wondering whether it is possible to use the so-called model-based approach. Let's say, for example, so-called structure-aware deep learning or topology-aware model, so that you can incorporate organ models in this process.
Yeah, I think that's another direction. Even for the lung nodal detection, there are so many other methods. First, detect the lung first. So in that case, we don't need to focus on other organs. So
okay.
that's a trend. People are also doing that. Yeah.
Okay, thank you. Any other question? 好，那我们再次感谢那个田老师的精彩报告。好，我们这个 session 就到此结束了。今天下午呢还有很多的精彩报告哈，有 Web 3.0与 AI 的终极对创，多模态大模型与跨境电商，从 GPT 爆炸中诞生的 SaaS 等专场，请大家关注。好，今天感谢大家带到现在哈，也感谢今天分享的嘉宾，好，谢谢大家。